So, good morning, ladies and gentlemen. I'm John McDermid from the University of Liverpool. I've worked in safety and complex control systems for over 30 years, and from January 2018 I run a program called the Assuring Autonomy International program, which is looking at how we assure and regulate robotics and autonomous systems. And I want to talk about moving towards producing a framework for assuring this class of systems. I want to start off just by saying, see, this is a very broad, multidisciplinary challenge. There are many technical issues, including use of AI and machine learning, but some of the first examples I will give are actually of autonomous systems that don't involve machine learning. There are ethical issues that we heard about yesterday, and also regulatory and legal challenges, and a little bit of a social perspective on these as well. So that's far too broad for me to cover in 20 minutes. So my aim is to take a technical perspective and very briefly come back to those broader issues in the conclusions. I'm going to start off with some motivating examples and then talk about some of the things we're going to build on in terms of building this framework. The title says towards a framework, so it's something that we want to put together. We have bits of, but it's not all there yet. But the solution elements give you some idea of what we're building on, and then some brief conclusions. And I'll try to link a little bit to what Richard said earlier. So my motivation, the second point is an analysis of safety risk assessment. The other three are examples of accidents that have occurred with autonomous systems of various sorts that help motivate why we want to build the framework that we're trying to do. So the first example is a military unmanned air system, a drone called Watchkeeper. The picture gives you an idea of what this little aircraft looks like. This was subject to a classical safety process. I'll say more about those in a moment. But basically, people look for hazards, what might go wrong, how likely they would to occur. 5 of these have been crashed in the first 15,000 hours. That's round about 3 orders of magnitude worse than the analysis says. So they weren't very close, and I'm going to come back to that in a moment. Talking to the designers about this, they perceive this little picture that I've got on the right as some of the underlying causes of this. So the green is how they designed the system and how they analysed it. The yellow is what actually happens in operation, so emergent behaviour, if you like, but what it actually does is quite different from what they thought it did. I don't think I've got a pointer, but some of the reasons for this are the environments it's in isn't what they expected. There are some design errors, but also things failed in a way that they didn't anticipate. So this is an autonomous system, which of course means there's 5 people on the ground monitoring it, because it's very complicated, and their perception of what it was doing was different to both how it was designed and what it actually did. And so they had problems both of observability and controllability. Interesting, I wasn't sure in your taxonomy you had observability, but that's certainly one of the problems in oversight. But also they were very busy, and so they had lots of documentation on how it works, but they actually just talked to one another about what was happening, because there wasn't enough time to read the documents to make decisions in the time frames. So at least one of these 5 accidents, the operators crashed it, but they crashed it because they didn't understand what it was actually doing and took what they thought was the correct action in the state of the system as they understood it. It just had to be wrong. I will speed up. So some years ago, a colleague, Drew Ray, and I, and a couple of others, did an analysis of quantitative risk analysis that really underlies most safety analysis. When you fly on a civil aircraft, it's been certified that the catastrophic hazard, things that lose the aeroplane, won't occur more than once every 1,000 million hours. And actually, they're pretty good. They're better than 1 every 10 million complete loss of the aircraft. But actually what we did is we looked at primary and secondary literature on this, and actually none of the numbers are right, trustworthy at all. And we stratified the reasons why this was the case and then produced a model that said, here are the fundamental things. If you don't fix these are the level 1 things. Then don't worry about the others because you're building on sand. Here are the level 2 and so on. And some of our level 2 issues are shown here. As this didn't focus on AI, but it worked perfectly well. So one of the first things, 2.3, is mismatch between the risk assessment and reality. Familiar, eh? And because an incorrect or misunderstood description of the system, that occurs very often. 2.4 is models that are used outside their valid scope. Does that sound like distributional shift? So although these were done for non-AI systems, actually many of the things that we identified, I think, also apply to autonomous systems that involve AI and machine learning. So to car accidents, this Tesla, as you may remember, basically the car couldn't decide whether to stay on the main highway or turn off the exit ramp, and went into the end of this concrete wall dividing the two roads. Now, I don't know how Tesla does their planning, but all the car manufacturers I know use reinforcement learning for this type of activity, and it couldn't decide which way to go, and did exactly the wrong thing. Is you going one way or the other, you stay alive. Going down the middle, you don't. So there's a problem there. Yesterday, one or two people talked about problems of perception. That's interesting. It didn't move. Let me try again. Thank you. So this is the Uber fatality in Tempe, Arizona. Actually, there is a video of this. The picture's harrowing enough, but the video is pretty horrible. But you can find it online if you wish. So these are problems of perception. Just over 6 seconds out, the vehicle detected some object. Over the next 5 seconds or so, the classification of the object changed, and at 1.3 seconds from impact, decided it was something for which emergency braking was needed. But the responsibility for that was with the safety driver, and she actually only hit the brakes after the impact with the pedestrian and the bicycle. So it's not an automated function, although it is actually on the base Volvo, which they modify. So this shows some of the problems of perception. Most perception systems, in fact all that I know of, are based on deep neural networks. So there's another class of algorithm you have to be able to verify. I don't know what the underlying technical cause of this was, but it's actually very easy to imagine what might have happened, that actually the system knows what a bicycle is, it knows what a person is, but actually the person pushing the bicycle might not have been in the training data set. So it took a long time to realize this. As a safety engineer, my view is, I don't know what it is, I put a bounding box around it and don't go into it. And I don't actually know why the system wasn't designed like that. To me, that would be a really basic piece of good design. Anyway, let me press on. Talk about some elements of the framework we're going to come to. So the first thing is there's a guy called Eric Hollnagel, probably not familiar to many people here. He's a bit of a guru in safety, and he characterizes the type of safety I was talking about, this risk assessment model. He calls it Safety 1, and it focuses on eliminating failures and errors, and that's necessary, continues to be necessary. But he talks about Safety 2, which is a focus on reinforcing what goes right. And if I contrast this with driving, typically people quote more than 90% of car accidents, fatalities are caused by human error. How many of you have ever, in driving a car, taken an action that's avoided an accident or made it not as bad as it would have been otherwise? Oh, come on, more of you. Yeah. The answer is it's probably 100% of you who drive, but it's just a normal part of driving. You don't realize that you've done it. And actually, we avoid accidents by doing the right things, including social cognition and thinking, gee, that guy's not going to stop at that junction, it's my right of way, I'm going to back off. And he makes a really important distinction that I do want to build on. He talks about the work as imagined. These are our models of the system, but also the analysis we do on those models to try to work out how they might go wrong. And then the work is done. What actually happens, where and when it happens. And these are normally different. If you think about my little watchkeeper example, there was a difference there between what was imagined and what actually happened. But in his philosophy, if you like, the way we improve safety is by reducing the gaps between the work is done and the work is imagined. Neither of these things are absolute. Sometimes as humans we do things that weren't in the plan, and actually that's good, and we actually make things safer or better as a consequence. But actually sometimes the rules were sensible, they were there for a reason, and people violate them and really ought to follow the rules more. So he talks about trying to reduce these gaps. So remember that. I'm going to switch into something that's much more familiar probably to most of the people here, which looks much more like machine learning. So this is out of a paper. Actually, in the proceedings there's a short position paper there, and I referred to this here. A couple of my colleagues in York and a visitor that we have to the program have been building this model of autonomous systems. So the bit at the bottom says we have a system in the environment, it monitors that environment, analyzes it, makes a plan, executes things, affects the environment, iterates around and goes that. So this monitor, analyze, plan, execute is a cyclic operation. The analysis can be done in traditional ways, or we might use machine learning, perhaps deep neural networks to understand images. We do our deciding using perhaps machine learning, maybe using reinforcement learning to do planning, and so on. One of the reasons for drawing this is that, in essence, the safety standards we have now around software assume I write a specification, I do a V development model, I do testing, and I show at the end all is well. Actually, bits of the system are still like that. The actuators tend to be quite conventional, but actually the machine learning parts is completely useless. It isn't how we build systems at all. We do, oh, that's interesting. This machine does have life of its own, doesn't it? I think it's saying that you're going too slow, McDermid, speed up. But I need to pause on this one. So we've got a life cycle, which is data management, the actual model learning, verification with iteration around. I'm not going to pick apart all of these, but I will pick up the model learning bit in just a moment. But what I want to point out here is reducing this model on the basis if you're going to assure things, you need to know something about the different elements of these models. And let me just pick out one thing on the data management. So it talks about data collection from operational data, but also augmentation. There are many things that are actually too dangerous. I don't want to go and run over 100 3-year-olds chasing out into the road after a football in order to get data to train the vehicles. I want to do that in simulation. So I need real-world data, but I also need to use simulation to augment that. And one of the interesting aspects of how I do this is how I get good enough coverage of the space using real data and augmented data. So let me press on, since the machine is suggesting that I should. So this paper has done a very broad survey of methods and techniques and so on relevant to these areas. So this is the model learning part, and what it said is that there's 4 subparts of this: model selection, training, hyperparameter selection, which is crucially important, and transfer learning. Can I move this to other domains? And gone through with a sort of systematic search, trying to find relevant material. What we also have done in the paper is set out some desiderata criteria in better, easier English that these things ought to satisfy. So they should have good performance, be performant, be robust, be reusable, be interpretable in some sense. And I'll come back to that maybe later if we have time. So try to identify which of these things help in these particular areas. And this paper is submitted for publication. It's on archive at present, and it'd be really good if some of the AI specialists here would go and look at this and tell us things that we've missed or misunderstood. But what it also does is it identifies what we believe to be, gaps in the literature, in the understanding. So if you, pick up things like reusability, one of the issues that we don't understand is how to identify, sufficient similarity in models so that we can actually use one model in another place and so on. So try to identify some of these open challenges as well. And so what we're doing is using this sort of information and others to help us build a body of knowledge which reflects both that machine learning life cycle and this system structure. In actually some senses it's very different to what Richard was saying, but in a different perspective it's very similar. There's a big element about verification, and even bigger element about validation, which I quite agree is a much, much bigger problem. I have some colleagues who do formal verification, and I keep irritating them by telling them, oh, that's the easy bit, it's validation that's really tough. Actually, you're right, verification is really hard too, but validation I think is worse. It's a tree structure, which is also cross-linked, so there are some similarities, but many of the labels of the nodes are different. For each of these we try to say, well, if I'm interested in verifying the understanding part of some image analysis system, what objectives do I have to meet? What approaches are known to demonstrating that? And also contextual information. Let me just illustrate that by means of a practical example. I had a phone call a few weeks ago with some guys who said, hey, they knew how to verify object classification algorithms in such a way that you could use it on land-based systems, autonomous vehicles, in ships, in the air. And I decided after their conversation with them that it wasn't true, but that would have been really interesting if you could, because it would say, actually that works in many domains, but often the context information is saying, actually it works in this domain, but doesn't work in that. And if you think object classification on land is hard, try it at sea, because the road doesn't move and change direction, and you don't get all sorts of reflections and so on, so it's really tough. So as initial online version, the structure we hope is reasonably stable. The contents certainly aren't, it's going to evolve. What it also includes is an outline safety case. So actually I'll move on to the next slide in a moment. For those who are not from a safety background, so a safety case is a justification why some system is safe or safe enough to use in a particular operational context. We normally represent that by having an argument which we produce in a graphical structure to make it clear, and then it's supported by technical evidence at the bottom. And this is a tiny fragment, not very interesting, it's just a straight decomposition here. I've got a more elaborate example in a moment. This is part of a verification element. What's interesting is really these little black blobs and the side arguments. These are about confidence, and these confidence arguments have to help me explain how I've overcome some of the intrinsic difficulties of training my ML system, avoiding biases, and so on. And what we hope we'll be able to do in time is to refine this pattern so it's more widely usable. But to me it's an open question whether we can produce a single general model that's widely applicable, or it needs to be domain specific. So let me tell you about the framework and give you a little illustration before I go on to the conclusion. So our framework looks like this. I talked about Hollnagel Safety 1 and Safety 2. So here you've got the real world that the work has done in his terms, and I call it the world as opposed to the work as imagined, which is up here. What we've added to this, it'd be interesting to have your thoughts on it, is this notion of the world as observed. One of the reasons for introducing that is to say that most of these autonomous systems are incredibly data rich. If there's a difference between what we imagine, what we design the system to do, how we analyze it, and how it behaves, can't we go and look at the data in the system and find out what it actually did? Now that's not going to be a perfect representation of the real world, but it's the best we've got. So actually, can we then go and use machine learning to analyze this data, find out what's actually happening as opposed to what we thought was going to happen? And what we can then do is extract information from that into the safety case, compare what we thought would happen with what's actually happening, and use that to help reduce the gaps, increase safety in the way that Huang said. So if we can do that, then we have this ability to get feedback from these differences, discrepancies we see between what we imagine and what actually happens, to feedback to change the design, change operational procedures, change data collection because of things that we can't actually determine. So it's a way of actually getting a better handle on how we achieve safety. And let me just, I'm going to go back a slide and just pause for a moment. What this is saying is, in a different way, is we build systems that are so complicated, we can't do this bit and get it right. And actually, that's true now. The reason, our analysis of quantitative risk analysis says these numbers are never true. That says we can't even do it now for normal systems. But if they are more complicated and also learn, there's no way you can do that and get it right. And if they learn in operation, you definitely can't do it because they're going to change their behavior. So you actually have to look at the real world as well, and to try to understand the differences and reduce them as appropriate. And it says here, machine learning is a partial solution. The data is far too complex for human scrutiny, so I think you need to use the power of machine learning to analyze this. And I've got an example of that in just a moment. So, in terms of the safety case, then, the initial version would be quite classical, based on the sort of analysis that I mentioned earlier, but it also has to talk about some of the gaps that are identified in the model, the assumptions that are made, the limitations in training data sets. And what you would want to see in the safety case is an argument that those are managed so that they're small enough that we're confident that we can deploy the system. We then expect it to evolve, being updated based on analysis of the world as observed, or the work as observed, and that will support feedback of various ways. Now, somebody yesterday, sorry, I meant to check my notes, I forget who, talked about actually doing dynamic assessment of safety. But I think ultimately you would want to be able to do things dynamically, and maybe the system carries its own model of risk and makes decisions based on those internal models of risk. I don't think we'll do that very soon, but actually some of our research is looking at those sorts of issues as well. There's then a regulatory perspective. I mean, this varies from domain to domain, but for example, if you talk about getting an aircraft into the sky, the Federal Aviation Administration or EASA in Europe or wherever will check what you have done, at some point say, that is good enough to enter service. And this is normally a one-way decision gate. You say, yes, this aircraft is good enough to enter service, and you only revise that on the basis of a major design change or following an accident. And the 737 MAX is a classic example of this, where there's an approval given, which has been withdrawn. Now there's been a serious enough accident. Now, I think these processes are really untenable with autonomous systems, simply where they will actually carry on learning in process, learning in operation. You can't make that one-off decision and allow them to continue operating. And actually, as you saw from our analysis of quantitative risk assessment, they're pretty much challenged now. So what this means, I think, is that the regulatory processes need to be much more incremental, much more subtle. There will be some initial approval based on the work as imagined, but actually that needs to be updated based on the work as observed as these systems operate. Now, I've been talking to some regulators about this who aren't entirely unhappy with this as an idea, but they're very unhappy about their ability to do it because of the resources and expertise it needs. But to be honest, if we're going to regulate safety of these things, in time the regulatory framework is going to have to change. Now, I said towards, this model isn't completely without validation, but the validation is not on an autonomous system as yet. So this is work that the second author, Yang Jia, is a PhD student working with us on some medical systems, but actually the machine learning part on the world as observed is what she's been working on. So let me very briefly explain this example. So it's a medical example dealing with medication safety following surgery on the chest, thoracic surgery. One of the biggest risks here is heart problems, atrial fibrillation, AF in this picture if you can read it. So what was, and this is a safety case fragment I'll explain in a moment. So what was done is that we did analysis of hazards and hazard causes on safety analysis on the work as imagined. Those of you who understand the way that the medics work, they'll find what they call a pathway, which is actually how they treat somebody for certain conditions. Our safety case starts with the top goal of preventing or controlling atrial fibrillation, and the things at the side include information about the setting in an intensive care unit, what sorts of things you'd expect there. The medication safety process has got 4 stages. You prescribe a drug, you dispense it, you administer, you give it, and then you monitor what happens. These little rhomboids are a strategy which is explaining how I'm going to go about showing I've met these goals. What we've amplified is administering the actual giving of the drug here, and what we said here was going to argue over hazards, and there are examples of 4 types of hazard here. The worst one is the one that we've looked at in detail, which is emission. There's a type of drug known as beta blocker, and in particular, if you have beta blocker before the operation, the medical guidance is you should carry on having it afterwards, but it doesn't always happen. So that's the one we focused on because it's the most severe hazard. So we've looked at how we demonstrate we meet this goal of ensuring that we do give the beta blocker, there is not this emission. That's done in the context of the safety analysis in the work as imagined, and then an analysis in the work as observed of the hazard causes. So this has been done by using Bayesian network structure learning to identify the dependencies in the data that comes from the hospital, comes from the ICU. That's interesting. It showed 2 things. One is that actually some of the medical advice about giving beta blockers is indeed right. It reduces the probability of atrial fibrillation, which can lead to death, by a factor of nearly 2 in some cases, and certainly clinically significant in the data sets that we've seen. But actually it also, there was a gap, a discrepancy between what was in the data and what the analysis said. Actually, one of the causal dependencies we expected to see wasn't there. And there isn't time to explain why, but we're able to unpick why that was. And this safety case actually reflects the resolution of the 2 different views, the workers imagined and the workers observed. So it's only a fragmentary example, but it shows that you can get some benefit out of looking at this real world data in this way. So conclusions. Actually, analysing artificial intelligence, autonomous systems can't be done adequately, effectively using our current safety assurance processes. In the framework we have, what we're trying to do is to reflect conventional safety processes on the sort of workers, imagine the design models we have, so on. But actually with the need to take care over those things that make machine learning based systems different from conventional systems. It then gets augmented and supported by analysis of data from the system in operation. So in a way, the very first talk yesterday was talking about using evolutionary learning to help solve problems. This is not quite the same. We're trying to say actually we can use machine learning to help address some of the challenges as well as them posing challenges. And so I said I would very briefly come back to the other things. I've talked a couple of times about gaps between what we imagine and reality. We've also been using this analogy looking at sort of ethical and legal or regulatory issues and believe there's some merit in that perspective. So from an ethical perspective, you can find responsibility gaps. If you transfer decision making to a machine, you can find you no longer know who is responsible for that decision from an ethical perspective, but also a legal perspective. And we think that gives some interesting viewpoints on how you might design or constrain the design of these sorts of systems. And maybe that will extend to social things too, but we've not looked at that. So hopefully that might give an interesting basis for discussion about how we go about assuring and regulating autonomy. And so this work's been funded in part by the Lloyd's Register Foundation and the university, but also the work I mentioned by Yan Jia is supported by one of our local hospitals. So, ladies and gentlemen,